Very good afternoon to all of you. Let's start with today's class. Saturday late afternoon is quite a unusual time to have a lecture. Nevertheless, let's do it. Good afternoon, Jemo. Good afternoon, Nimishka. I hope you people are great. Today's class, we are going to talk further from where we left in the last class. I'm going to discuss an overview of amplifiers and tuners. Both the topics are fairly elaborate topics, and both the topics are complete topics in themselves, in a sense that they are a complete course in themselves, and it would be highly unrealistic to expect that we are going to do them in detail in this course. We are not. But as a layman perspective, or from a person who learns a little bit about these equipments, we have to acquire that familiarity. So that is what we are going to do in this course. Nothing is in detail over here. And look at some of the problems which are fairly simple. Amplifiers, you have already heard the name. Remember, if you recall, you have learnt about a CE amplifier, which is called common emitter amplifier, and you have also read about, or you have also worked on something called as operational amplifier or op amps. So you already know, you are familiar with a few things about amplifiers. So here the names are different. There's something called as a preamplifier. Preamplifier amplifies a small microphone signal. Remember, the microphone pickup is very small. It will be in millivolts. Example, if you have a microphone, you speak into it, put a voltmeter on the other end and measure the voltage, you will find that the voltage that it is generating is is a is even less than a millivolt. It will be like 0.5 millivolt or something. It's a fairly weak voltage. So it needs to be amplified immediately so that the pickup becomes strong. And to amplify, the amplifier which does that job is normally referred as preamplifier. It is different from another amplifier to whom the user has an access. So in musical systems like TV, etc., the amplifier actually controls the volume. So for example, if you that's why the loudspeakers typically are coupled with amplifiers. So you increase the volume, you turn a knob on a small box. That small box is typically called as an amplifier. So now the coupling is different. Sometimes preamplifier is directly connected to the microphone. Sometimes preamplifier is kept as a separate box. Sometimes preamplifier is coupled with amplifier. So there are various possible ways of connecting them. But nevertheless, these are the important stages. Number one, a microphone. Number two, a preamplifier. And number three, an amplifier. An amplifier can have different gains for different frequencies and volumes as well. We'll come into details about it little later, but just to specify the point that the preamplifier has the same gain for all the frequencies. The job of preamplifier is just to amplify or strengthen the signal a little bit. An amplifier can have different gains for different frequencies. So for example, sometimes some speakers may require stronger bass, or some speakers require stronger higher frequencies. So amplifier can vary in their gains for different frequencies. Similarly, the the volume, the loudness level, etc., will decide the gain at different levels. Sometimes at a higher volume, the or a higher loudness level, you get lot of noise or lot of distortion. So in order to reduce the distortion, you in decrease the gain. Now, impedance matching is a very important thing when you are connecting. There are a number of parameters that I'm going to discuss very quickly, through which the system has to go through before we uh, before all the systems are placed together. So first one is impedance matching. So the impedance matching is important stage. The impedance of microphone, impedance of preamplifier, and impedance of the amplifier. They all should match. Typically, if the impedance of an input device is less, then it loads the next device. Loading, as you all know, is a flow of high current, and that may destroy the circuit. Therefore, impedance matching is important. If you remember, when we spoke about microphones in the last class, we spoke of some microphones like dynamic microphones having less impedance, while some other microphones have large impedance. Then the power matching. Remember, at one stage you are increasing the power of your circuit, so that has to be uh, done in a very coherent manner. So your very little power is generated in the microphone. Preamplifiers improves the power level by a certain amount, and then the amplifier again improves the power level by a certain amount. So at each stage you need to provide some sort of power source in order to improve the power levels. Then there could be various filters which can be applied, as we have discussed: volume, bass, treble, high frequencies, loudness, balance. If you have more than one speaker system, then you have to connect multiple amplifiers to multiple speakers. The volume controls are logarithmic most of the time, but when you rotate the knob, or a say a tune on a knob on a tuner or a volume control, it is almost appears linear. So you need to put some converters, some controls there also. So these are the important things. Loudness is controlling intensities over frequencies. Remember how loud it can be depends on the frequencies. We have done that long back. So when you are designing a musical system, the loudness has to be adjusted over the frequencies. Now the amplifiers do suffer harmonic distortion. It is typically referred as total harmonic distortion, or THD. Now, what is a harmonic distortion? To be simple, suppose I gave a pure sine wave as an input to an amplifier. What is expected from the output? So, obviously, if you are giving a pure sine wave at the input, you expect a pure sine wave at the output. That's what a true amplifier does. However, if you give a pure sine wave as the input, and the output, if you analyze in Fourier transform, if you get more than one sine waves, more than one component, frequency component, then we say that there is a harmonic distortion that has occurred. It can occur due to many reasons, and I'm going to discuss some of them. Now, total harmonic distortion is the sum is calculated. We are not getting into that calculation. Remember, as I said, we are just taking an overview. But total harmonic distortion, if you want to look at, you have to look at all the frequencies which are being generated. In some calculation, THD should be less than 0.05% for a very good amplifier. Power amplifiers, well, the word power amplifier comes here. Remember, we are all talking about power amplifiers are typically current amplifiers. So we are all talking about current amplifiers. The current amplifier improves the current in the circuit, and basically you need lot of current because all loudspeakers are current driven devices. If you have seen the last chapter, then we know that the loudspeakers are driven by current. So loudspeakers are current driven devices. They're all blocked like black boxes to normal people. Only experts and engineers work in it. Most of the people, for us, like amplifiers come with two knobs. One is the input knob, one is the output knob, and two controls, maybe left, right, and the volume up, down. So that's it. Input impedance of a typical amplifier can run into 50 kilo ohms. Input signal level is 1.5 volts. So look at this. This is important. Input signal level for an amplifier is around 1.5 volt, and then it can further amplify it to 5 volt or 10 volt, whatever. But remember, the from the microphone the output is in millivolts. So there has to be a circuit which converts that millivolt to around 1 or 1.5 volt. That is the job of pre-amplifier. That's what we have already discussed. The signal to noise ratio for a good amplifier has to be around 100 dB so that it does not pick up spurious noise as the signal is being processed. Linearity is an important parameter. If you have done your CA amplifier and if you have drawn the load line in your earlier experiments or projects or wherever, then you know that the linearity of the load line decides the amplification factor. So if the load line is not linear, the amplification will not be perfect. So that's what do we mean by linearity? So that's an important consideration. This is a typical frequency response. This diagram gives you the example of two frequency responses by which the gain is adjusted. The upper one is something in which the mid frequencies 400 to 2 kilohertz are suppressed while the lower frequencies are enhanced and even the higher frequencies are enhanced. So this is one typical frequency response generally used for pop music, etc. This kind of uh, frequency response. In this one, the lower frequencies are cut, bass is cut, treble is cut, only the center frequencies are enhanced, generally used for speech and some of the live performances, etc. So these are two just examples. There could be many such curves which most of the times either the earlier there were knobs in each frequency range. You can raise them or lower them to adjust the frequency response and subsequently the output. Then what happens is then software took it over. In the software, if you have used Winamp, it's an old, very old music player, and if you look at some old version of Winamp, then these controls were all software, and in fact there were many presets available, so by which you just go to the preset and say you want a classical music or a rock music, and it will adjust the curves automatically. No, but those days are gone. At the present day, what it is doing is uh, the software itself recognizes what kind of music it is, and depending on what kind of music, the software decides what kind of gain control needs to be applied. So we have come a long way as far as amplifier characteristics are concerned. Now the amplifiers suffer due to heat generation. Lot of energy is wasted. Class A amplifier, like your CE amplifier, is one which generates a lot of heat because it always works in the active region. Although it offers a very good frequency response, all Class A amplifiers, but the heat generation is very high and that's a drawback. In fact, they can be used in standalone system. Class A amplifiers are not an issue where the electrical power is available separately. But in systems where like mobile phones, etc., where the battery power is limited, the class A amplifiers do become an issue. And therefore we can go to class B amplifier, which has low heat production, and we have which has the poor frequency response, and therefore there's a third category which uses the mix of the two, which is class A and class B. It is called class AB amplifier, which generally improves the frequency response with low heat production. Whatever heat is produced, it is removed from the system by using metallic heat sinks, either of aluminum or good copper, and some fans suitably if needed. So I would recommend you to read an overview of class A, class B, class AB amplifiers. This is about the harmonic distortion. The creation of harmonic distortion is straightforward. This is the input. If this is the input, you can see this is a pure input. Now, pure sinusoidal wave, but output can be distorted. So let's say that this is my output. Now, if you look at it, this is slightly flat at the top. Okay, so it resembles like a square wave. It does not, I mean, partially a square wave, not completely. So obviously, if this is your input, which is a pure frequency, then of f, then the output will have along with f with number of harmonics. So these are all distortion harmonics. These are harmonics which were not needed. They will also play and they will change the pitch of the sound completely. So that's a main problem over here. Clipping of waveforms. The other is the intermodulation distortion. So this is my output. There is a base low frequency which is modulated with a high frequency, or whichever way you look at a high frequency being modulated with a low frequency. Now even when this happens, there can be some distorted output, and you, instead of getting just one sideband, you can get a number of pairs of sideband, and this could be another source of distortion. These are called sum and difference frequencies. And there are transient distortions, like whenever the state change is there, like from here to here, especially in class AB amplifier, then you will get a spike at the ends because of some spurious voltage coming in, and that will going to distort your output. So there are various reasons by which frequency components of the output may change because of the input, and these kind of distortions will come in the category of what is called total harmonic distortion. Next is the AM/FM tuners. So AM tuners, you are familiar. I mean, in fact, you are familiar with both, so nothing is new. There's a high frequency carrier, low frequency audio. AM modulator changes the amplitude with frequency like this. AM generally operates in 540 kilohertz to 1600 kilohertz, and between two channels of AM there is a frequency gap of 10 kilohertz. That is important. It has a 5 kilohertz bandwidth. Very high fidelity is not possible. AM is prone to, first of all, bandwidth is poor, so data transfer of data, amount of data transferred per unit time is less, and secondly, high fidelity is not possible. It is prone to lot of spurious signals, because most of the spurious signals get attached with the amplitude only, so it gets corrupted and the reception is not clear. So AM is replaced by FM. FM, as you all know, is varying the carrier frequency with respect to audio frequency. So wherever the audio signal is strong, let's say, the frequency will increase. Wherever the audio signal is poor, the frequency will drop. So you can get a low frequency, high frequency, low frequency, high frequency, etc. The frequencies for FM vary from 88 megahertz to 108 megahertz. You know, you must be familiar with the names of the various FM channels. They are actually advertised with their frequencies like 98.3 or 104.7, etc. So these are all the frequencies channels between these two. Here the gap is little larger between two channels, 0.2 megahertz, and the bandwidth is around 75 kilohertz. So a lot of clear, noise-free propagation of signal is possible. Even the stereo signal is possible because stereo, as you know, left channel and right channel. So even that transmission is possible in FM tuners. It is not possible in AM tuners. Okay, we finished with that. We finished the discussion. Let's look at some of the simple problems. What are the advantages and disadvantages of using microphones of low impedance as compared to those of a high impedance? So I think we have discussed this earlier as well. A low impedance will increase the sensitivity of the microphone, but it has a chance of loading the next stage. So a high impedance microphone, a low impedance microphone like a what you call a dynamic microphone, a high impedance microphone like a capacitive microphone or a condenser as we call it, can be used. So it has a high impedance, so it is better. So we have discussed it. Why would Dolby Digital give more realistic sound than Dolby Pro Logic? Dolby was a very interesting company. You know that it's a I'm not giving the answer to this because it's a commercial question basically. You need to just Google it and figure it out that what commercial systems are doing. But I have a very interesting story to tell you about Dolby. The Dolby started his systems. Dolby Incorporation started with a very simple idea. Now, when the magnetic tapes arrived, cassette players, I suppose many of you must have seen the cassette players. The cassette players had a magnetic tape in them, and those magnetic tapes, the recording was done in the form of ferromagnetic material, orientation of ferromagnetic material. And there was a reed head. So whenever the cassette has to be played, a button needs to be pressed, which used to press a reed head on the tape against a pad. And the tape used to squeeze through the gap in between. And the reed head used to pick up those patterns and generate sound, generate current, which eventually was converted into sound. Now, those in that reading, the reed head, when it was moving over the tape, because of the friction, there was a hissing sound, a very faint, not as loud as I'm saying, but a very, very faint hissing sound used to come. In fact, if you still have a recording of a cassette player and if you listen to it, you can make out that hissing sound distinctly, and that can be used to determine whether it's a cassette player or not. In fact, even before cassette player, when there were vinyl records, a needle used to rub along at the vinyl records, and again there was a hissing sound, but that characteristics was slightly different than this one. So Dolby realized that sound, he analyzed that and figured out that it is some at around 4 kilohertz or 5 kilohertz. And then when the signal was being amplified, he actually suppressed that particular frequency, and the resulting output sound was much better. And he patented the system and marketed it with that special technology. And that's how the Dolby was born. Later on, Dolby created Dolby Surround, which by which you have multiple speakers, and then many more ways they try to improve. In fact, if you are a movie watcher and last this corona period, I'm suppose nobody's watching movies in the theater, but if you have seen movies in the theater, then almost most of the movies will come with a Dolby logo, because mostly the chance is that the movies has been processed by Dolby laboratories. So that is what you have to look into, that what is the difference between Dolby Digital and Dolby Pro Logic. These are the very recent technologies developed by them. A microphone has a sensitivity listed as 1.2 millivolt per Pascal, an output impedance of 200 ohms. What is the open circuit voltage sensitivity in dBV? What is the power sensitivity in dBm? What is EIA sensitivity in dBm? Another problem is a microphone has a sensitivity listed is minus 56.6 dB and a 600 ohms output impedance. What is the voltage sensitivity and what is the open circuit voltage with the singer singing at 102 dB? So both of these problems can be solved by using the formulae which we have developed in the last class. So I don't think we have to go through it right now. You can go through it and compare the voltage output from the two microphones. Microphone A has a sensitivity minus 60 dB per volt per Pascal, and microphone B has a sensitivity of minus 66 compared to the same reference. So please look at these problems. They are simple application of the formulae. This is voltage sensitivity 20 log V by P. This is the developed voltage. This is pressure which is in Pascal. And the power sensitivity, once you get SV, you can calculate SP dBm and both the calculation. An 8 ohms loudspeaker is capable of handling 30 watt audio power. So you can see that resistance is given and power is given. So power is I square R. So if you know R and P, you can calculate maximum current. So how much current will flow when it is receiving 30 watt of power? So that can be calculated. What should be the size of the fuse or the circuit breaker? So that also you can check in the data sheet. I think we addressed this problem even earlier. So with this we finish this chapter as well, and we can stop this lecture today. Thank you.